the ways that fusion is currently a immature, early stage emerging industry comprised mostly of vertical integrators, and that there's a tremendous need and tremendous opportunity for a more mature, more well-rounded kind of supply chain and ecosystem of vendors, suppliers, original equipment manufacturers, and so on and so forth, across everything from materials to components to consumables to systems and subsystems to software and human and financial services. Basically, across every single piece of the industry, there are places for corporations, entrepreneurs, investors, researchers to make a difference. And that, I think, is the message that has not been heard enough.
Your trusted source for information on the energy transition. This is the Insider's Guide to Energy podcast. Welcome to another edition of the Insider's Guide to Energy. I'm your host, Chris Sass, and with me is co-host Jeff McCauley. Jeff, what do we have happening today?
It's about time to talk about nuclear fusion. And this is such a big topic. We have two guests joining us today, not just to talk about the innovations enabling fusion, but the systems of enabling innovation in fusion, which is super meta. And I'm really excited to dig in with our two guests today. We've got David Cohen-Tanugi, venture builder at MIT as part of Proto Ventures, and Richard Pearson, co-founder and chief innovator and UK director at Kyoto Fusioneering, who gets the title for longest title so far, I think we've had on the show. David, Richard, welcome. We're so thrilled to have you here.
Yeah, thanks for having us.
It's great to be here.
So first of all, this is a new program out of MIT, Proto Ventures. We want to hear a little bit about what that is, David, and then maybe how you first came to collaborate with Richard, and we'll dive into fusion from there.
Excellent. Well, very happy to start. So just a little bit about myself for background. I'm a climate tech entrepreneur. I did my PhD in materials science and engineering, actually right here at MIT about a decade ago. And I've worked on technology commercialization ever since. Out of grad school, I co-founded a startup called Amber Labs together with some classmates. Then I went on to lead the automation team at a virtual power plant startup called OhmConnect. And so now I lead the clean energy efforts for MIT Proto Ventures. Proto Ventures is MIT's in-house venture studio. To our knowledge, the first of its kind program within any university. Basically, what we do is we create new projects within the university that have the potential to change the world of energy and to become successful startups. So we do that by combining technologies and ideas and people that we see on the MIT campus with real world pressing commercial needs in the clean energy sector. We had a first channel focused on AI and healthcare a few years ago that resulted in the creation of two companies. And for the last year or so, we have really been laser focused on innovations in the clean energy sector. We do this primarily in collaboration with the MIT Plasma Science and Fusion Center, which is a major research center on the MIT campus that works primarily on fusion, but really touches innovations and areas of science and engineering that have potential and applications for other parts of clean energy. So to your question, Jeff, I originally met Richard as part of the community of fusion energy commercialization folks who across universities and startups and now increasingly large corporations are really trying to see how we might make fusion energy a reality at scale.
Wonderful. And Richard, tell us a little bit about your background and how you came to meet David and why you're contributing to an MIT project
absolutely.
Across the pond.
So first of all, I am across the pond. I'm British. I guess a bit about me is I started life as a mechanical engineer, but then went on to study nuclear engineering at Imperial College, where I got my master's degree. I then went on to complete a PhD in fusion engineering and innovation, and that was at the Open University in the UK. And my expertise there is broadly on fusion engineering and innovation, but really my central focus was sort of around systems thinking on fusion commercialization specifically. I still hold a couple of visiting research positions and a field editor position at a journal, so still engaged very much in that area as well. And that sort of is how I met and came across David. So I've been aware of David's work for a little while now, and we thought very similarly. So a lot of the work that David did going into the report that I think we'll get into a little later was very much dovetailed with what the work I was doing, and also overlaps heavily with the thinking and the way that I viewed the fusion world, should we say. My role, so in 2019, just as I was finishing my PhD, I started a fusion company in Japan. Now, that's a whole other story, how a British person in Britain started a company in Japan, or rather co-founded a company in Japan. But essentially what we do is we're a privately funded fusion company. We've raised, I think, around about 100 million US dollars equivalent now in capital. And we are a bit different in the sense that if you think about fusion, which I think we're probably going to have to take a step back at some point to talk about what fusion is, but if you think about fusion as being like a star in a jar, most of the organizations you hear about are focusing primarily on the star and sort of will build out to the jar. But we're focused on making the star work by designing systems and technologies that go into the jar. And again, we can get into the specifics of that a little later, but our mission is kind of to unlock the potential of fusion by enabling the sector to deliver that ultimate energy source that is fusion. And as you said at the top of the call, I have 3 titles. UK Director, I manage the UK team trying to grow us over here. But my Chief Innovator role is really a technology to market kind of role. So looking at productization, trying to think around how we foster those relationships that ultimately result in new collaborations, partnerships, and supporting the cutting edge fusion sector.
This is wonderful. And so I want to dive into this report that you've highlighted. It's enabling commercial fusion, venture, and technology opportunities for a growing fusion industry. This is possibly one of the best technical reports I've ever read. It is accessible, it's bite size, it's breaking down an extremely complex topic into accessible areas. It's basically what I would call the innovator's guide to fusion. So if you're an entrepreneur or a systems thinker and you're looking for ways to contribute to fusion commercialization, this is your guidebook of where to start. It actually borders on industrial policy, and it's one of the more comprehensive documents I've seen. If this was coming from any other source, if it was coming from a national lab, it would probably be 300 pages, but it's very accessible. And what stands out to me is exactly what you were highlighting, Richard, which is when people think about fusion, they think about these groundbreaking science experiments in a lab somewhere that's either using magnets or lasers or this or that, just to show, hey, we can get break-even energy for 1 femtosecond or something. What's really exciting about this report is that it really is treating fusion as a system and a commercial system that needs multiple technologies to work for it to reach commercialization. So I've said enough glowing praise about this report, but I think this highlights, and David, I want to ask you, how was this conceived of as the output? Because most venture studios don't have this kind of overarching industrial policy in mind when they start. Was there a template or something that you were starting from that led you to envision this report?
Well, thank you for thank you for the kind words, Jeff. I'll just first say this report was a lot of fun and a really great collaboration between a lot of highly expert and talented people. Definitely more knowledge, people who are much more talented, intelligent, and knowledgeable than I am. So if anything, I just coordinated a bunch of folks and kind of helped go from an idea to reality. Okay, so what is this all about? And to your question, Jeff, how does a venture studio inside of a university create a opportunities report that starts feeling almost more like industrial policy? The mission of Proto Ventures is to create startups that wouldn't have existed otherwise and that have the potential to change a field, an industry, in our case, clean energy. And as a result, I, coming in about a year ago, was interested and quite intent on not just doing what a lot of clean energy tech commercialization consists of, namely looking at technologies and basically focusing on what people call tech push. Here's a promising breakthrough. I think it's useful for something. Let me go and try to find what it's useful for, and then we'll make a product and sell to it. My experience of commercialization in general and of the clean energy sector in particular is that that really has its limitations. And so we were very intentional in kind of setting up the clean energy channel at Proto Ventures, that we were going to take a really broad look at what the overall space looked like today and what were the biggest bloggers and ultimately the biggest levers for both kind of changing the industry and ultimately making the biggest impact and building the most successful companies. So that's what really motivated spending multiple months really in more market discovery, customer discovery, opportunity assessment mode before jumping into any specific venture idea. And as we were doing this, interviewing leaders at existing clean energy fusion startup companies and other people, investors in the space and other folks in the sector, what became very apparent was that fusion has gone very quickly over the last few years from basically an academic research area to now a real commercial effort with dozens of private companies having raised billions of dollars at this point to develop fusion power plants, with very ambitious goals to deliver power to the grid in the early 2030s, and commercial plants later in that decade. So these are very ambitious targets, with companies that are well funded and putting a lot of effort. But what was also apparent is that these companies, as much as they want to be relatively vertically integrated and be essentially the developers and the providers of a whole power plant design, like Richard was saying earlier, they have a sense of what their core is, and their core typically is kind of the star, making a plasma and producing net energy gain and so on and so forth. But they end up having to focus on many, many, many different areas that they don't view as their core, but that nobody else is doing. And the truth is, all mature industries need and leverage a robust and sophisticated supply chain. I can't really think of any industry that doesn't meet that criteria. And most people who've studied industrial innovation believe that fusion eventually will be no exception. There may be integrator companies, picture the equivalent of Boeing, say, for aircraft. But there's going to be people who make airplane seats and people who make engines and people who make, the little screens that you use to watch TV and so on and so forth. And it's not relevant. It's not realistic for Boeing to try to do that all by themselves. And in the same way in the fusion industry, that won't be realistic either. But today, the fusion industry is shaped is in a very immature way, let's put it, where we only have Boeings. There's basically Boeings and a couple small entities that aspire to be the engine providers or the seat providers or the control systems providers and so on. And I would say Kyoto Fusioneering, Richard's company, is really the poster child, I guess, for forward-thinking entities that want to fill out that ecosystem. So long story short, having accumulated that knowledge about what's needed, where are the gaps, and what are the things that fusion companies really wish they could purchase from somebody else, and know it's going to bite them eventually because they don't have time to work on it today, but they're going to be blocked until somebody else can sell it to them, and nobody's slated to do that. We at Proto Ventures decided to partner with the Plasma Science and Fusion Center at MIT to create an external facing roadmap, inviting really as a call to action, really, entrepreneurs, investors, researchers, national labs, large corporations that would be tempted to create a new business unit, all these folks to look at this industry and realize that there are opportunities for them to make a big impact and be financially successful, hopefully in the long run.
But David, when I first met you, I think it was at an MIT event not so long ago, and pretty much everybody on stage was talking about this ecosystem of the parts, right? Two things that came to mind. One, you just threw out a few numbers, and same with Richard. Your billion here or dollars and things. These numbers sound tremendously large to the layperson, but where we're going, they aren't very large, I guess. First, let's quantify exactly what we're talking about, this ecosystem and the economies of scale that are needed to achieve perhaps fusion. Assuming we get through the science risk and we get there by 2030 and have a commercialized solution, what are the economies of scale? What kind of numbers are we talking? Because I think it's deceiving to our audience just to hear, Commonwealth Fusion, big dollars, this guy, these dollars. But what does that mean?
Yeah, sure. No, it's a great point. I think, therefore, probably the best place to start here is saying we are talking about creating an entirely new industry here. Yes, it's an energy technology, but what will stand up this new energy technology is a whole new industry. So I think it's instructive to go back to sort of pre-aviation era and thinking what was required to get to commercial aviation in the first place. That's kind of what we're talking about here. That's the paradigm that we're in. So, we're not talking about someone being a new, let's just say, car manufacturer, and they want to bring in, they're a new company, they want to bring a new type of car to the market. So several examples of that over recent years. That's different because the market's there already. The product, in the case of companies like Tesla, maybe they're vertically integrating new ideas, but fundamentally, we've designed wheels before. We've designed chassis before and so on. So there's a lot of pedigree knowledge there. Here, we're talking about trailblazing pretty much everything. We're saying we need to develop this, we need to develop that. And that goes from everything from supply chains through to new mining, new manufacturing techniques, as well as all the actual fusion stuff itself. So yeah, orders of magnitude more cash going to be needed here than the billions. It's going to be a tens of billions or into a hundreds of billions industry over the next decades. That's going to grow, and it is growing at the moment. That's the positive thing, but it needs to continue that growth, and that's going to require both public and private investment globally as well.
The second trend that I noticed along the way was a lot of fusion companies. So Richard, you seem to have started out understanding that there's a supply chain needed and an ecosystem needed and trying to solve that problem. What I've seen with a number of the early fusion companies, 130, 160, whatever number you want to say of funded companies, is a lot of them think they're going to make magnets. They're going to make other products in order to get some cash flow during the next 10 years or whatever they need. How does this vision change from what you and David are talking about here? Is that what this is, or is that something different?
I think this is something different. I think what you're referring to, Chris, is the tiering of the market roadmap of certain fusion companies that say, in the long run, we're a fusion power plant company, but that's going to take a while to get to revenue. So in the meantime, we're going to sell other stuff. Another great example, and actually it's the poster child of fusion here at MIT is Commonwealth Fusion Systems, which started out in their early stage pitches saying exactly what you were saying, namely, we can also sell magnets for other applications. And even if fusion doesn't work out, we'll still be a successful company because we'll sell magnets. So it's not just a timing thing, it's also a de-risking thing inside out.
I'm going to try an analogy here. Been thinking about this while David was speaking just there. What we're talking about here is an industry that is maturing at the moment and going through a phase of companies having been around for a few years and having had a reasonable amount of investment, some a lot more than others. And there's some soul searching going on for sure. But then let's think about, let's compare fusion to the Mars shot. And I specifically use Mars shot there actually, because I think the mission to Mars is probably the only thing that comes close to being the sort of technical challenge we're talking about here, sort of akin to the level of technical complexity. So someone's going for the Mars shot and they are fully down that path. Someone might go, actually, hang on a minute. I think I can help them get out of orbit. Or actually, hang on a minute, there's an entirely separate industry of satellite technologies that need to go to orbit. I think I'm actually going to do something different. I think I'm going to turn into a satellite orbiting company. Others may go, well, actually, I think we can mine the moon. We've got technology for that. So by helping someone try and get to Mars, you can both help them do that, whilst also stopping off along the way and realizing there are commercial opportunities on that quite literal path through the stratosphere, up into orbit, onto the moon and beyond. So I think maybe there's an interesting analogy there. Maybe I'll try and build on that in the future. But I think that's where we're at the moment, where there are companies realizing, okay, I have mining technology. Okay, I've actually got the satellite technology you're talking about. I can help you with designing your payload structure, whatever it may be. So there's a bunch of things here that in fusion are shaking out at the moment. And I think David's report, coming back to that, does really well at identifying the system that we currently exist in and where those opportunities for innovation sit.
Can we keep going on that and maybe some more examples? Because I believe there's another, what is it? It's like a millimeter wave laser technology that's being used in geothermal. I'm probably getting the technology wrong.
Yes.
What am I thinking of? Is that Quaise?
Yeah, Quaise Energy uses.
Well, I was going to say, I
You
think,
go ahead,
so
Richard.
yes, that's Quaise Energy, an interesting geothermal company, again, with some affiliation, I think, to MIT, or at least some background and certainly strong geothermal research at MIT. So yeah, Quaise Energy is a geothermal company, and they're looking to use a fusion-relevant technology called a gyrotron, which I'll talk about in just a second. But basically, they want to use that technology for a different application, and that's to pulverize the Earth's crust, to try and do drilling without actually using any mechanical components. So a gyrotron is a high power, high frequency microwave emitting device that, being a microwave at the right frequency, can resonate and cause and create heat. So it can heat up matter. In the context of fusion, what we use gyrotrons for is to heat a plasma. So if you tune to the right frequency and you have the right power, you can actually heat the ions in the plasma, and actually provide energy to that plasma to get to the right conditions for fusion to occur. What we're talking about here is a complete spin-off application for this, where 5 years ago, if you'd said this to me, I would have said, wow, that sounds really crazy. We can't do that. We can't use it for essentially mining operations. But that is now being looked into, which is a really interesting spin-off application, including for Kyoto Fusioneering, by the way, because we make gyrotrons.
That's great. So I want to talk about timeline and then go to what might be the next examples. So first of all, we did throw around the timeframe 2030. I want to clarify that these are research reactors in the next decade. When we talk about commercial fusion, I don't think anybody's talking about that being a reality before 2050. So to use the Mars analogy, our question here is, can there be decent businesses getting satellite into orbit for the next 10 or 20 years, and then those turn into amazing businesses if we are going to Mars in 20 to 30 years? So the example here in fusion being, could you have a advanced laser technology that enables geothermal in the next 10 to 20 and then is there to support fusion in 2050? But help me with the time frames, and then I want to get into what might be those next example businesses.
Well, let me describe a little bit the methodology that we took in the Enabling Commercial Fusion report, and I think it will help answer this question. Ultimately, what our report, the question that our report asks and answers is, if there is to be a commercially successful, large-scale, mature fusion industry one day, if that is to happen, what will have to be true? What products, goods, services, components, subsystems will have to exist and be available for that industry to be mature and functional? And then we laid out all of those things. And some of those things are not available today, and they're really an invitation to researchers to start working on potential solutions. Others are things that could be built tomorrow if only the relevant entities put their mind to it, and so on and so forth. And so that's on the kind of the supply side of things in terms of what's available and what will be available. And then there's a demand question, which is what I think you're asking fundamentally, Jeff, which is, what is there demand for today? What is there going to be demand for in 5 years? And when is there going to be the full demand, as in like a big, full, mature, successful, lucrative fusion industry? I think what I would tell you is, you will hear a wide range of estimates about when fusion becomes not just a club of startups, but actually, producing power on the grid and meaningfully displacing other sources of energy in the global energy mix and everything. Nobody knows is the short answer. I think the hard-nosed, people's best guess, I think, who are not directly in the fusion startups, would probably tell you, if things go well, we start seeing the first electrons being produced and going onto the grid in the late 2030s, and the first commercially viable money-making plants showing up in the 2040s, such that by the time the second half of the 21st century is rolling on, 2050 and beyond, then the size of the fusion slice in the energy pie starts becoming visible and starts crowding out the other parts of that pie. So that's roughly, I think, the timeline, assuming things work out. And that means, to your point, Jeff, there are some things that you should not try to start selling today, because actually you'll only really be able to sell those things in 2030 or 2040 or 2050, which is maybe not what an entrepreneur would want to do today. And there are other things, on the other hand, that are very much in demand today. And in my market research and customer discovery in the fusion space, I identified a number of places, and this is not called out explicitly in the report, that actually there's ripe for a startup today, and there's a demand for it today. I'll list a few, and Richard, I'll let you add as well, because I suspect you have a strong hypothesis around this. Standards and ratings for the investment community to wrap its head around what all these different fusion companies are doing and claiming, and being able to independently assess what is real and what is not real, and compare apples to apples. Picture Moody's or Standard & Poor for fusion. There's a market for that today. A mega fund for fusion investments, similarly, so that everybody who wants to get in on the action but doesn't have the technical expertise to vet all the different opportunities, there's a market for that today. Workforce training and recruiting, just to get qualified human beings and brains working on this tremendous challenge, there's a market for that today. Cryogenic systems, materials testing, sensors, there's a market for all of these things today. And it doesn't mean the market's not going to get bigger. It hopefully will, but you could very well make a company selling just in fusion with that in the near term. Richard, what did I miss?
Yeah, but that's good, because you've teed me up. But I think it's probably worth saying that I agree with everything you've said. I think just to take one side step or a step backwards to the point about sort of going for that commercial fusion and why that's still the goal. I think it is really imperative to point out that people are excited about fusion because this is last energy. That this is there. We don't need to go on the hunt for another energy source after this. It's not like, oh, we've done fusion, what's next? All those sci-fi films we watch where there's flying cars and mega cities and sort of no one seems to be worried about pollution or anything like that. All of those kind of utopian societies are often implicitly fueled by something like fusion, clean, plentiful, etc. So when we've done this, as David says, that pie, that slice of the fusion slice of the pie that starts to grow will only grow and grow and grow. And that's not just for electrification, by the way. That'll be for deep decarbonization. So I just wanted, before I dive into some of the other areas, including the ones that we're working on in the current markets and potential future markets, I think it's really important to sort of note that point.
Let's keep going in and hear a little bit about what you're currently working on.
So I agree. The areas that David laid out there are ripe for innovation, particularly the ones around investment, and actually sort of almost the diagnosis is, well, the industry's growing and we've got to this point. How do we check we can go to the next phase? That's where some of those come in. Then there are some more, well, they're mainly deep tech related. So one of the things we're working on, for example, is the tritium systems or the fueling system. So let me use another car analogy here, if you'll let me. So if you think about an engine, you have to inject fuel into the engine. The engine uses that fuel to produce the power, and then you can drive the car. Okay. However, it's more complicated than that, because if you go down to the component level, you realize, okay, we need an injector that can inject at a certain rate. We need sensors that tell us how much fuel's in the tank, how to get the fuel from the tank to there. And then you need an exhaust system. There is a reason you put catalytic converters on exhaust, because there's certain waste products and so on. Now, imagine that, but about, well, infinitely, I don't want to say infinitely in literal terms, but many, many times harder with a lot more complexity. And we haven't done this before in this way. So one of the things we're doing is we are actually building and demonstrating these technologies work, not just independently, which meant much of the research over the last, certainly the last 30, 40 years by public sector has looked into, but we're actually trying to commercialize these technologies. And we're building a facility called Unity 2. Unity 1's in Japan. Unity 2 is in Canada. Unity 2 is a tritium fuel cycle test facility. So tritium is the fuel for fusion, and we're going to actually be testing this in an integrated fashion. And this is going to be both our own test facility to demonstrate that and also a user facility. So looking at the commercial angle, we're saying to the sector, come and work with us. We will help you design, develop, and qualify either your own technology, or we're actually able to pivot our technologies towards what you need. So this is sort of, engineering product development in action. So we're converting that pure R&D focus into something that the market needs right now. So I think probably that's the best example of what we're doing. And of course, we've touched on gyrotrons already.
Yeah. And Richard, we've probably waited long enough for you to give us an actual definition of fusion and maybe use the significance of tritium and deuterium in your answer.
Okay, great. Other talks are available on exactly how fusion works, but I'll try and give a sort of a summary. So, in no small terms, fusion is the process that powers the sun and the stars. And I like to tell younger students that I've taught in the past, we're all made of stardust, and therefore we're all made by fusion, because every element in the known universe, apart from those that are produced by supernovae of stars, comes originally from either the Big Bang or from fusion reactions. It's the densest form of energy in the known universe, and it's the opposite of fission. So in fission, we split the atom. In fusion, we try to combine lighter elements. And in that process of doing so, we actually release huge amounts of energy. So that's how fusion works at a fundamental level. Now, in stars, that's actually quite easy because they've got the right conditions for that to occur naturally. Although, interestingly and somewhat counterintuitively, stars actually burn their fuel quite slowly. That's why the sun has lasted for millennia and will continue to do so for multiple millions and billions of years still. On Earth, we can't recreate those exact same conditions, so we have to mimic them in a different way. And what you essentially do by that is you use different fuels. So in the sun, you start with hydrogen and helium. On Earth, we use two isotopes of hydrogen: heavy hydrogen, which is deuterium, which is available in seawater, and tritium, which is super heavy hydrogen. I won't get into the specifics of the reaction there, but basically, this is the easiest one to get to the right conditions to do fusion. How? Well, simply, we basically heat up a mixture of these two hydrogen isotopes hot enough so that it turns into a plasma. Plasma is an ionized gas, fourth state of matter. It's going back to high school physics there. When an element is ionized, those electrons are removed, and you only have the nucleus left. So the resulting ionized nuclei are positively charged. Okay, so you remember positively charged things often like to repel. So that's why fusion is hard, because we can't actually get these things to join together unless we get this plasma to be hot enough, dense enough, and last long enough. And for fusion on Earth, it's that combination, the so-called triple product. This is the so-called Lawson criterion in physics terms. Basically, you've got to get that above a certain threshold, and various approaches. So you've heard CFS mentioned, Commonwealth Fusion Systems, David mentioned earlier. That's a magnetic approach. So what they're trying to do is to get it hot enough and actually last long enough. So they're trying to hold that plasma for a long time. But it's actually not very dense. So they're just trying to get those conditions jacked up. Whereas if you look at like a laser approach, they're trying to go hot enough and dense enough, but they're not holding it for very long at all. It's a pulsed, continuous approach. So there's different ways of doing this, but that's essentially what we're trying to do on Earth. And when we get above that point where we can make fusion happen, that's what I think, Jeff, you referred earlier to as break even. This is when you get more power out of the fusion reaction than you put into your magnets, your lasers, your heating systems, etc., to actually give the conditions in the first place. David, did I miss anything? Jeff, Chris, did that make sense to you? I think it's probably a good place to stop.
Made sense to me.
I'll just add one piece if that's all right. We haven't we've said implicitly but not explicitly why people in the energy space are excited about fusion, and that is because fusion's been essentially a holy grail of the energy sector, because it promises firm, dispatchable energy with no operational CO2 emissions, and in a dense form factor. I guess maybe those are the top four. So firm, dispatchable, no operational CO2 emissions, dense form factor. And I guess if you were to add more benefits that get people excited about fusion, it doesn't inherently require the use of high-level radioactive material, unlike nuclear fission, and it doesn't rely on a scarce or critically limited fuel, like pretty much any fossil energy production technology. Just because something is a holy grail doesn't mean it's easy to attain or going to work out necessarily, but generally there's an interest in seeing whether we could power society in this at least in theory, much better way.
So I have one more question before we try to pull this all together. I've got two believers on this podcast today. Fusion's been around quite a while. It's you have degrees in fusion, so you went to school. It's been around long enough that we have degrees and things in it. Help me understand why now. What's transformative today that means this is a reality or a near-term reality that 23rd we're going to have these proof of concepts, in 2050 we'll be enjoying free ubiquitous energy.
I should be very clear that there's a high I should be very clear that it's absolutely possible that the dream, the holy grail of fusion, is not attained in our lifetimes, or never, or that it is attained and turns out not to be economically competitive with other energy sources. There are many different things that could turn out not to be true, and that's not a reason not to be optimistic. But I don't consider myself a fusion salesperson, and I don't think that Richard does either. So there are reasons, however, to be optimistic, and the reasons why now, the reasons why things that have not worked out in the past and promises that were broken in the past may turn out to be true this time around include the advent of high temperature superconducting materials that enable much stronger magnets, which then themselves enable much denser, more modular, smaller, and more cost-effective fusion systems. A willingness to invest tremendous amounts of energy and funding, honestly, into the energy sources of the future, including from the early stage, high risk venture capital community. I think those are probably two reasons of multiple why fusion may happen now that it hasn't been before. And I guess the third thing I would add is scientific breakthroughs recently in the fusion science community that really leave scientists and engineers feeling like we understand more about the science of fusion and of plasmas than we ever have before. So a lot of barriers, engineering barriers and science barriers, to be honest. But people are generally feeling more optimistic than they have.
Yeah, I compliment that. And so I compliment that by saying there was a very famous Soviet physicist actually called Lev Artsimovich, and he said in something like the 1970s, fusion will be ready when society needs it. And I think it's becoming clearer to me what he meant by that is there has to be an actual market demand, a real demand to make fusion happen. So fusion has been in the remit of government labs around the world for the last 75 years. This is not a new thing. This is since the 1950s. This has really been looked at in earnest. There was a spike in funding after the oil crisis in the late 1970s and so on. And there have been sort of comings and goings of funding, but it's kind of been in the remit of the public labs to say, hey, we're doing some interesting research here. And we've learned a lot about the science of plasmas and about fusion as a whole. But we've had a number of things along the way that really suggest that essentially this wasn't really about commercialization all along. And it would be commercialized when ready. I think we're at the point now where what we've seen is a paradigm shift. We've seen a paradigm shift in the way that we're doing things. So actually, if you read my thesis, please don't. It's too long and laborious. But my thesis, I contend that we are in this paradigm shift right now. This is an entire upending of the way we're doing things. And this is basically saying we need to get to something that's actually usable for society, not just profitable, by the way. The definition of innovation is the useful application of invention. And that in the context of fusion means potentially incredibly lucrative for investors, potentially massively transformational for society and for the planet. So this ticks so many boxes. And I think where we're at right now is it's just that change in, hang on, we've done loads of really good science here. We've got a lot of good ideas. We understand the fundamentals. Nothing we look at and go, well, we don't understand the problem. We may not always have the solution, but there's nothing we look at and go, we have almost no idea what's going on there. There are some exceptions to that, but I'm going to caveat by saying we're not going to go into those now. But generally speaking, we think we can find solutions to these known problems. And by commercially orienting them, we're saying, let's get to that solution faster, better, cheaper. And that really is the philosophy of the private sector. And actually, this paradigm shift that we've seen over the last, I would say, certainly over the last 5 years, but it's been nascent for 10 years, and it's now coming to a head. Public sector's now reoriented itself to say, actually, we want to support you. We've got that data, we've got those scientists, we've got those capabilities. Can we help you deliver your mission and be part of the story here again? Because I'm not saying public sector's ever gone out of the light, but there was almost I wouldn't say a race, but it was a quasi race between public and private. Now it is really, they are coming together in a meaningful way.
This is really inspiring. Thank you both for joining us. I think we've got a view here where fusion has maybe been called the fuel of the future, but always will be. And now we've got a path for fusion to come out of the lab and actually become a true commercialized energy technology. And we see the systems and subsystems that can even be businesses today. And Commonwealth Fusion showed us there's $2 billion of investment that have been made, and that's not going to be the last one. So for listeners, if you're an entrepreneur, you're an engineer, you're an investor, fusion is not relegated always to be several decades away. There are ways that those underlying tools can be useful businesses right now. Thank you, David, Richard, so much for joining us today. This has really been educational and inspiring.
Thank you for having me.
For our audience, we hope you've enjoyed this episode of The Insider's Guide to Energy. It's been fun making it. The one thing you can do for us if you like this content is take the time to hit the like button, the subscribe, follow button, and add comments and questions. Our guests love to see your feedback. And we'll see you again next time on The Insider's Guide to Energy. Bye for now.